Okay, so let's talk about the thermodynamics of gases. So let's start with heat capacity. Heat capacities. So this is heat capacities. So we have the heat capacity. So what is actually meant by heat capacity? So heat capacity is defined as the heat required. So our heat is actually denoted as Q, heat required to raise the temperature of the substance by 1K. So the heat capacity is defined as the heat required to raise the temperature of the substance by 1K. So the formula given is actually Q is equal to C theta. So this delta T is actually meant by increase in temperature. So this is increase in temperature, just like so. So this is the meaning for heat capacity. So what about the definition for specific heat capacity? So let me just erase this one first, and this one as well. So specific heat capacity okay. So just now is the capital letter C now, and this one should be the small letter c. Is the heat required? So heat is actually Q as well. So heat required to raise the temperature of 1 kg of the substance by 1K. So this is the specific heat capacity, which is the heat required to raise the temperature of 1 kg of the substance by 1K. So the formula given is actually Q is actually equals to mc delta T. So this delta T same as the T from the heat capacity, which is increase in temperature. Alright, so this is the definition for specific heat capacity. Okay, so let me erase this one first. Okay, this one as well. So what is the difference between the heat capacity and specific heat capacity? So as for the heat capacity actually aim for the total mass of the substance. So heat capacity is aim for the total mass of the substance, which to increase the temperature of the substance by 1K. As for the specific heat capacity, so this is the capital letter C, specific heat capacity, which is the small c. So specific heat capacity is actually aimed for the 1 kg of the substance. So specific heat capacity actually works for to raise the temperature of 1 kg of the substance. So, as for the heat capacity is to raise the temperature of the substance by 1 K. So that's the difference between heat capacity and specific heat capacity. So as for the relation between this capital letter C and small c, so let me just use another color. So this C is actually equals to the MC. So this C is for the specific heat capacity, and this one is for the heat capacity. So this will be their relation. Alright, we have done for specific heat capacities. So okay, let me just erase all this one. Alright, so let's just move on to another parts. So as for the object, we have heat capacity. So what if our how should I describe that? Our subject is actually gas instead of object. So gas, we know that gas actually we usually calculate in terms of moles. As for the object, we have the mass. So since the gas has the smaller mass, since the gas has smaller mass, so hence mole is used to represent mass. So actually, we usually calculate the gas in terms of moles, which same with the water, or we can say liquid. So gas and liquid we usually calculate in terms of moles. Alright, so since we calculate the gas in terms of moles, so so let me just erase this one. Okay. Alright, so since we calculate the gas in terms of moles, so what we have is actually the molar mass. Molar, wait for a second. So we have molar heat capacity. So this molar heat capacity divided into two different conditions. So which for the first one, we raise the temperature of the gas molecule, not gas molecule, we raise the temperature of 1 mole of gas molecule at constant volume. So as for the another one, we raise the temperature of 1 mole of gas by 1 K at constant pressure. So this is the two different conditions for the molar heat capacity of the gas. Okay, so we will explain it one by one. So let's just start with the molar heat capacity at constant volume. Okay, so at constant volume. So what is actually the definition for molar heat capacity at constant volume? So it is actually defined as the heat. So our heat basically is Q, the heat required to raise 1 mole of gas, sorry, to raise the temperature of 1 mole of gas, 1 mole of gas, so to raise the temperature of 1 mole of gas by 1 K. So 1 K is actually 1 Kelvin, so in full name, at constant volume. So this is the definition of molar heat capacity of at constant volume. So let's say I have a container. So this is my container. So there will be the gas inside the container. So let's say I apply the heat to this container. So basically we know that the gas will gain kinetic energy, but in the condition of the volume of the container must be constant. So this is the definition for molar heat capacity. Alright, so we have done for this first condition of molar heat capacity. So let's just Alright, so let's just move to the second condition, which is the molar heat capacity at constant pressure. So as for the definition, molar heat capacity at constant pressure is actually defined as, so the sentence is actually the same as the molar heat capacity at constant volume, but at the end of the sentence is actually at the constant pressure. So let me just write it down. Defined as the heat required to raise the temperature of 1 mole of gas by 1 K at constant pressure. So this is the definition for the molar heat capacity at constant pressure. Oh, I missed the formula for the molar heat capacity at constant volume, but it's okay. So let's just explain the formula for this definition. So Q is actually N CPM delta T. So N is our mole. So N is mole. So this CPM is actually the specific heat capacity. Okay, so let me just scroll it down. Specific heat capacity of 1 mole of gas, at constant pressure. So this T, we know that is increase in temperature. So let's say our mole is actually 1 mole. As for our T, increase in temperature is actually 1 K, since the definition is 1 K. So the specific heat capacity for so the heat required to increase 1 mole of gas by 1 K is actually equals to Q equals to CPM. So this is the heat required for the 1 mole of gas to increase the temperature by 1 K. Okay, so this is the definition for molar heat capacity at constant pressure. So just now we missed about the formula for molar mass heat capacity at constant volume. So let's just go through it. So let me just erase this one first. Alright. Okay, so as for the constant volume, we have Q is actually equals to N CVm delta T. So this is the for heat required to raise the temperature of 1 mole of gas by 1 K at constant volume. So let's say my mole is actually 1 mole according to the definition. So okay, so this is delta T. So my delta T is actually 1 K. So what we have is actually the heat required to raise the 1 mole of gas, to raise the temperature of 1 mole of gas by 1 K at constant volume. So this is the definition for molar mass heat capacity at constant volume. Alright, so this is how we determine the molar mass heat capacity at constant volume. Okay, so we have done for these two conditions. Alright, so I think we have done for the parts of heat capacities. So let's just move on to another parts. So as for the next part, which is the work done by the gas, Alright, so work done by the gas. Okay. So, okay. Before that, we need to know, let's say I have a piston here. So this is my piston, and this is the, okay, something pull, okay. So this is the section which the barriers for the gas molecule to prevent the gas molecule out from this pistons. Okay, so let's say I have my gas molecule here. So, okay, so let's say I supply the heat into this system. So my heat is actually Q. So we know that if the temperature of the gas molecule increase, so basically the gas will gain more kinetic energy. As the gas gain more kinetic energy, so this gas molecule will eventually collide with the wall of the pistons. So this is the wall of the pistons. So they will collide with the wall of pistons. So let's say I have my initial volume, which is V1. So this is my V1 here. So as the gas molecule keep colliding with the wall of the piston, so this piston so this wall will eventually move to the V2. So this will be my V2. So okay. So from here we can see that there's a change in displacement. Alright, so this is okay. So there is the change in displacement after the collision between the wall and the gas. So what we have here is actually okay. So we know that the work done for the simplest equation of the work done is actually F delta X. So this delta X is the displacement. So okay. So we know that if the gas keep colliding with the wall, so this will eventually produce the pressure between the gas and the wall. So in this system, we can see that the pressure is actually related. So what we have here is actually P is equal to F over A. So our F is actually the rate of change in momentum between the gas molecule and the walls. Okay, so this is our PA. So let's just substitute this F into PA. So this is PA delta X. So what we have here is actually, so this A times this change in X, what we get is actually P delta V. So this is the work done by the gas. So this is what we call the work done by the gas. So let me just write it down. Work done by the gas. Alright, so from V1 to V2, that's actually the work done by the gas due to the increase in internal energy, or should I say kinetic energy of the gas. So increase in internal energy of the gas will eventually increase the collision between the gas and the wall of the pistons. So this wall of the piston will eventually move from the initial volume to the second volume. So since there's change in volume, hence there's a work done by the gas. Alright, so this is the basic definition for the work done by the gas. Okay, so there's actually three conditions, or should I say three process, which can be altered when work is done by the gas. So that when there's work done by the gas, so there's also one of the three condition occur. So as for the first one is actually isomeric process. So if there's work is so there's work done by the gas, but at the condition of constant volume. So isomeric process is actually meant by the constant volume. As for the second condition, we have isobaric process. So this isobaric process is meant by the condition of constant pressure. This is the second condition. So as for the third condition, we have isothermal process. Isothermal process, which is constant temperature. So we can say that there is probably one of the condition, which is constant volume, constant pressure, or the constant temperature, can be exist when the work is done by the gas. Okay, so let's just go through one by one. So let's just begin with the isomeric process. So, okay. So let's say I have my piston here. So this is as for the reference. So this is my wall of the pistons. Okay. So isomeric process, which is constant volume. So we can see that from the curve, we have the curve here, which is the PV graph. So this P is meant by the pressure and this V is meant by the volume. volume of the piston. So this is the volume of the piston. So from this graph, we can see that since the condition is the constant volume, so what we have here is actually a straight line. What we have is a straight line. So this is my V1. So since, oops, this should be V1. So this one is my V1. So since there is no change in temperature, so the straight line, the graph will represent a straight line, which is change in pressure, change in temperature, but the volume is constant. So since the volume is constant, hence we can conclude that our work done is actually equals to 0. Why? This is because the wall of the pistons is still at the same position. It means that there is no change in displacement. So there's no change in displacement, which is delta x. Hence, the work done is 0. Alright, so this is the isomeric process. Okay. So since the volume is the same, um, the only changes is the pressure and the temperature. Hence, the work done is actually equals to 0. Since there is no work is done by the gas to move the piston from the initial volume to the other volume. Alright, so this is the definition for isomeric process. Okay, so let's just move on to the second one, which is isobaric process. So isobaric process is the constant pressure. So as for the constant pressure, what we have in the graph, so let's say I pick a random value for the pressure. So let's say this is my P. So this, what we get is actually the straight line. So from this condition, the P for us is actually constant. As for V is changing. So let me just write a triangle to this V. As for the temperature is also changing. So V obviously is changing since the straight line is moved from V1 to V2. So the work done is actually the area under the So the work done is actually area under the graph. Okay, so we can conclude that our work done is actually the P times the change in volume. So what will be what will be our change in volume? So the change in volume is actually the V2 minus V1. So this is the work done by the gas at constant pressure. Alright, so this is the second one. So as for the third one, okay, let me just erase all this one. Okay, so as for the last one, we have isothermal process. So isothermal process is basically a constant temperature. Constant temperature. So in this case, we can know that the temperature is actually constant. As for the volume is changing and the pressure is also changing. So from in terms of graph, so since the graph of PV, so since it is a graph of PV and the volume and the pressure is keep changing, so what we have is actually the curve. But sometimes you may saw another curve. Not the curve should be a straight line. So this two graph, which is a straight line or we can say it is a curve, could probably exist. So the work done by the gas is actually okay, so let me just erase this one. So I use this first curve as the preference. So let's say this is my V1 and this is my V2. So the work done is actually the area under the graph. So the work done for me is actually the integration of V2 and V1. So this is the P delta V. Okay, so alright, so let me just scroll it down. Okay, so as for the P delta V, so okay, so let me check for a moment. Yeah, this is the P delta V. So we know that the PV is actually equals to nRT. So what we have here is actually the P equal to nRT over V. So what we can do is actually sub this nRT over V into this equation. So what we have is nRT over V dV. Okay, so from here we can observe that this tree is actually which is nRT is actually all are the constants. So and the mole is the constant and the molar mass constant is also a constant and the temperature is also the constant since it is the isothermal process. So what we can do is actually the move up this nRT into outside. So V2, V1, so this is 1 over V dV. So integration of 1 over V is actually ln V. So bracket V2, V1. So let me just continue it here. Okay. Oops. Okay, so what we have is okay. I missed something, which is the nRT. So this nRT, so what we have is actually the ln V2 minus the ln V1. So if we are about to change the base of ln, so the subtraction of the ln is actually equals to the division of the ln. So what we have finally is V2 over V1. So this is the work done by the gas at constant temperature. Okay, so we have done for all the three parts, all the three conditions. Okay, so let's just do a conclusion. At the constant pressure, not pressure, at the constant volume, the work done by the gas is actually 0. As for okay, we have our graph. So this is PV. So our graph is actually a straight line, which is parallel to the pressure axis. So as for the constant pressure, the work done for us is actually P V2 minus V1. So what we have is the horizontal straight line. So this is the vertical and this one is the horizontal. So as for the constant temperature, the work done by the gas is actually nRT ln V2 over V1. So the graph, we have two types of graph for this process, which both the pressure and volume varies. So okay, so for the first one, it's actually the curve. So okay, so this arrow is actually important, which means that the gas is actually moved from V1 to V2. So as for the second graph, it's actually a straight line. So this is a straight line. So okay. So these are the conclusion for all the three conditions, which including the graph. So this, for the first one, is the vertical graph, which is the constant volume. So the work done is 0 since the volume there's no change in volume. So as for the second condition, which is the constant pressure, so what we have is the horizontal straight line. So this is area under the graph. So this is the V1 to V2, which means that the piston moved from the initial volume to the final volume. So as for the third part, third process, which the pressure and both the pressure and volume also vary. So what we have is the curve graph or a straight line graph. So the work done is actually the area under the curve. So this is V1, this is V2, this is V1, and this is V2. Alright, so that's it for the work done by the gas. So we have done for all the work done by the gas. So let's just move on to the next parts. So have to note that there is actually the three condition, which is also the three process when the work is done by the gas under this one of the three condition. Okay. Oh, I missed a part. So let's just move on to that part first. Okay. So as for the combination of the three process, so this is our pressure and this is our volume. So for the first process, which is the constant volume. So what we have is actually the straight line. So this is my V1. So this is my V2. So as for the second process, this is our isothermal process. This is isothermal process. As for the third process, this is the isobaric process, which move back from V2 to V1. So the total work done is actually in this area. Is the region which bounded by the curve, and the straight line. So we can conclude that these three process can be occur simultaneously, but in the condition of step by steps. And so from this curve, for the first step, the pressure So this is the pressure of P2 and P1. Pressure increase from P1 to P2 at constant V. So we have the change in pressure, but in the condition of constant volume. So as for the second one, so as for the first part, of course, the temperature of, also change. So as for the second one, we have the isothermal process. So okay, so let me just think about for the sentence. So the volume changes isothermally, therm, isothermal, isothermally. So the volume changes isothermally from V1 to V2. So the volume changed from V1 to V2, and the pressure, I didn't state in this sentence, and the pressure actually go back from P2 to P1, but in the condition of constant temperature, which is isothermal process. So as for the third one, so I can say that the volume volume changes from V2 to V1 at constant pressure. So these are one of the example for the statement which the question will state, So this statement is not necessary, not should I say not necessary. It's not necessary the question will come out in this type of statement, but the question will ask in another form of statement, maybe. So we need to understand the concept and understand it step by step so that we are able to see which one is the process and which one is their condition. So that's it for the work done by the guests. So let's just move on to the next part. So we have done for the work done by the guests. So let's just move on to the new parts, which is the first law of thermodynamics. Thermodynamics. So let's just go through the definition first. So what is actually the first law of thermodynamics? So it actually states that the heat energy supplied to the gas, the heat energy supplied to the gas is equal to the increase in internal energy and the work done by the gas. So before I state the formula, I have to explain some of this from this statement. So let's say I have a piston again. So this is my pistons. So this is my gas molecules. Okay. So let's say if I supply my heat to this system, so eventually the gas will gain kinetic energy as we mentioned from the previous parts. So the gas, since the gas will gain the kinetic energy, so it will eventually collide with the wall, which is the same story from the previous parts. So after some collisions, so this wall of the piston will eventually move from here to here. So what we know from V1 to V2, so the wall of piston move from V1 to V2, there will be a work done. So I repeat again, when this heat is supplied to the gas, so the internal energy of the gas will increase. So the increase in internal energy will collide with the wall of the pistons. So after some collision, the wall of the piston will eventually move from the initial volume to the second volume. So this is what the first law of thermodynamics states, by saying that the Q is equal to the change in internal energy. So increase in internal energy will collide with the wall of the piston. So the wall of piston will eventually move from V1 to V2. So hence there's a work done by the gas. So this is the equation of the first law of thermodynamics, which is equal to increase in internal energy and the work done by the gas. So that's it for the definition of first law of thermodynamics. Okay, so let's just move on to the another parts. So we're still in the subtopic of first law of thermodynamics. So let's just go through the relation. Sorry. Okay. So let's just go through the relation of Cp and Cv. So before that, we need to know what is actually the Cp and Cv. So as we discussed from the previous part, we know that this is the specific heat capacity for the 1 mole of gas at constant pressure, and this is the specific heat capacity of 1 mole of gas at constant volume. So what we have here is actually the Cp and Cv. So what is actually meant by this? So this is meant by the specific heat capacity for one gas molecule at constant pressure. So this is actually the specific heat capacity for one gas molecule at constant pressure. As for the Cv, so the sentence is actually the same. So one gas molecule of course, but in the condition of constant volume. So this is the definition of Cp and Cv. Okay, so let's just move on to how can we prove the relation between the Cp and Cv. Okay, so oops. So for the first step to prove this this relation between the Cp and Cv, so for the first step we need to state the molar heat capacity at constant volume. Molar heat capacity at constant V. So we need to prove out the statement of the molar heat capacity at constant V in order to prove the relation of Cp and Cv. So from the first law of thermodynamics, we know that Q is actually equals to increase in internal energy plus the work done by the gas. So in this condition, which is the constant volume, so since the volume does not change, and we know that the work done is actually equals to 0. So from this equation, we actually can see that Q is actually equals to our internal energy of the gas. So basically, we can conclude that our internal energy of the gas is actually equals to the NCVM delta T, since Q is equal to the NCVM delta T. So since my mole is equal to 1 and the increase in temperature is also equals to 1K, so what we have for the internal energy of 1 mole of gas is actually equals to CVM. So this is the first information that we need. So let me just write here. Alright, so we have done for this parts of molar heat capacity at constant volume. So what if okay, let me just erase down. Okay, so let's just move on to the molar heat capacity at constant pressure. So we have to note that this, oops, okay, I missed one word. So have to note that this is the condition of constant pressure. So based on the first law of thermodynamics, which is Q equals to delta U plus, okay, let me just erase this one. Q is equal to delta U plus delta W. Okay, so my Q is actually equals to NCPM delta T, which is the molar heat capacity at constant pressure. So we, according to the definition, so heat required to raise the temperature of 1 mole of gas by 1K at constant pressure. So we use the definition as the preference. So our Q is actually equals to our molar heat capacity of 1 mole of gas at constant pressure. So this is Q equal to CPM. So let me just write down here. So remember, we're still in the condition of constant pressure. So I need to erase this one. So what we have is actually the CPM. So this U, we actually can sub this CVM into here. So I'll explain later why. So this work done is actually the change in work done, which is the P V2 minus V1. So this is the work done at the constant pressure we discussed from the previous parts. Okay, so why we can actually substitute this internal energy as CVM? This is because since both cases are increased in 1K in terms of T, in terms of delta T, hence the internal energy is equal to CVM for both cases. So since we use the 1 mole of gas and increase in 1K, so hence our internal energy for our gas molecules at constant pressure is also equals to CVM. So that is why we can substitute this CVM as the internal energy of the gas. Okay. So this can be cancelled. Okay. So this is the internal energy for our gas molecules at constant pressure, which the temperature is increased by 1K and we still use for 1 mole. So the increase in internal energy is CVM. As for the heat supply is CPM. So let's just continue. So this is CVM. So this one is actually the P delta V. So what we have is actually the P delta V is equal to NR delta T. So I can directly substitute this one as NR delta T. So why delta T? This is because at constant pressure, the volume and the temperature is keep changing. So since my N is actually 1 mole, so what I have is actually, and my T as well, is 1K, as we mentioned from the previous parts. So this CPM is equal to the CVM plus R. So since this one is 1 and this one is 1, so what we have is the relation between the CPM and CVM, which is CPM is equal to CVM plus R. So this is the relation. So we're still not done yet for our derivation. So as we observe from our equation, this is actually the CPM and this is actually the CVM, which is used to describe for 1 mole of gas, but our aim is actually for the specific heat capacity for one gas molecule at both constant pressure and constant volume. So what we can do is actually divide both sides by our molar mass. So this is our molar mass. So after dividing the molar mass, what we get is actually the Cp is equal to Cv plus R over M. So this is our true relation between the Cp and Cv. So we have done for this objective. So this is the relation that we need. Okay, so alright, so we have done for this relation. So let's just move on to our last part of this. So let me just erase this one. So let's just move on to our last part of this video. So there is more parts after this one. So ratio CP CV. So so this will be our last part of this video. I'll discuss the next parts in the next video. So let's just move on to this CP over CV. So same. And how we prove this CP over CV? So the first step, we need to relate the condition of constant volume. So so based on the first law of thermodynamics, so what we have, our work done is actually equals to 0. So Q is equal to the change in internal energy, and we discussed from the first previous part, which is the internal energy for 1 mole of gas, which is increased by 1K, is actually equals to CVM. So so this is the parts which we discussed from the previous one. So what we need to do is actually add more one part. So based on the previous chapter, which is the kinetic theory of gases, we know that the internal energy of the gas for 1 mole of molecules, not 1 mole of molecules, for 1 mole of gas, which is equals to the F over 2 nRT. So I should denote this as delta T. So since my N is 1 mole and my delta T is 1K, so what I have for my internal energy is actually equals to F over 2 R. So this is my internal energy. So this F is actually represents the degree of freedom, as we discussed from the previous chapter. So what we can do is actually substitute both sides, which is 1 is equal to 2. So my CVM is actually equals to F over 2 R. So this is the one that the information that I need. So let me just write it here. F over 2 R. So let me just erase all this one. So since we discussed from the previous part, we know that our CPM is actually equals to our CVM plus our ideal gas constant. So so what we can get for our CPM is actually my CVM is F over 2 R. So this is R. So I factorize this ideal gas constant. So what I get is F over 2 plus 1. So this is the another information, which is the CPM, which is equals to my bracket F over 2 plus 1 multiplied by the ideal gas constant. So we have this 2, and what we can do finally is we follow this ratio. Since this ratio is for one molecule, for one gas molecule, but my ratio, so let me just write it down here. So CPM over CVM. So this ratio is actually represent for 1 mole of gas. So but both of them is actually the same. So I can conclude that finally my Cp over Cv is actually equals to R F over 2 plus 1 divided by F over 2 R. So what I can do is cancel, and finally I'll get 1 plus 2 over F. So I simplify it, F plus 2 over F. So this is the ratio for the Cp and Cv. So why I mentioned that the CPM is actually equals to Cp equals divided by Cv. So this is because, so let me just write here in case you guys, in case you guys not able to remember, not able to understand. So okay, let me just move on to next here. So this is actually equals to the Cp times the Avogadro constant. So this is the Cv times the Avogadro constant. So my Avogadro constant times the specific heat capacity of one gas molecule at constant pressure. What I get is actually equals to the 1 mole of the specific heat capacity of 1 mole of gas at constant pressure. So this same goes to for the condition of constant volume. So this will be cancelled. So what I get is actually the Cp over Cv. So that's why I said that the Cp over Cv is actually equals to the Cpm over Cvm. Alright, so that's it for this video. So we will continue for the other parts in the next video. So if there's any question need to be asked, please comment below this video and I'll see you next time. So thank you. Bye.